Okay.
Please go ahead.
Okay, so thank you, Nima, and thank you for the kind invitation. I think it's a real pleasure to talk about the research that I do, and also some of the, and I'm also looking forward to the potentially interesting discussions after the talk. Right, so what I want to talk about today is mostly a deep learning acceleration. It's one of the primary reasons why people are looking at doing in-memory computing for. Right. So this is how I have. Oh, is something blocking your view, or?
We can see it.
Okay, because it's coming from Zoom, so I'm not sure if it's blocking or not. Yeah, that's fine.
Yeah.
Right. So, so this is how I've structured today's lecture. The first, I will briefly introduce computing systems for deep learning and in-memory computing. Then I will give an overview of in-memory computing using phase change memory in the context of conventional deep learning. And you can see the list of topics here. And finally, this is kind of like the forward-looking part of the talk, where we'll take a brief look at applications that go beyond conventional deep learning. So deep learning, as many of you know, had rather humble beginnings, right? In 1943, Warren McCulloch, who was a neuroscientist, and Walter Pitt, who was a logician, they created this very simple mathematical abstraction of a single neuron. The soma of the neuron is represented by a node that receives logical inputs via the dendrites. It aggregates them, and based on this, a decision is made and is output. So this is a very simple model that captures just the essence of what a biological neuron does. And of course, several years later, Rosenblatt showed that a slightly modified version of the McCulloch-Spitz neuron can actually perform linear classification, but that was kind of, the original perceptron was quite limited in its capability, and subsequent decades, of course, came the multi-layer perceptrons, which could now do non-linear classification tasks. And of course, one of the key breakthroughs was training such multi-layer perceptrons using gradient descent and backpropagation of errors. Then there was kind of a pause, but eventually we had enough compute power and availability of data to also make neural networks work with real-world tasks. It was indeed a very sudden development, as you know. Even in the early 2010s, people considered you crazy if you're doing artificial neural networks, and in fact, it was getting dropped off the curricula of many universities at that point in time. But in 2012, with the ImageNet contest, everything changed, and neural networks became a big success thereafter. So if you look at it at present, deep neural networks, they of course come close to or even outperform human beings in certain cognitive tasks, image and speech recognition, and they're also the mainstay of the AI portfolio of the major IT companies, including IBM. But we all know that deep learning has a serious problem. It is computationally intense. It takes days, if not weeks, to train state-of-the-art neural networks, even with the most advanced computing hardware. The power consumption is highly undesirable, and many accounts are unsustainable, right? As pointed out by some of these articles which came in MIT Technology Review. You can also think of it as, the world's costs don't increase exponentially, but deep learning applications are indeed increasing exponentially. So you can again see where that thinking comes from. If you look at many of the edge and end device deep learning applications, this kind of energy consumption is even prohibitive. Of course, computer architects have really woken up to this challenge. I mean, if you look at it, deep learning, I would argue, is one of the primary drivers for innovations in the field of computer architecture. A part of the innovations are still within the confines of conventional general-purpose computing systems. For example, technologies such as storage class memory and near-memory computing are being developed to tackle some aspects of AI acceleration. But as you know, the most active area of research and innovation right now is in the space of standalone accelerators that optimize the computation and data flow to achieve very high efficiency and throughput. However, this approach is already strained, given that we are living through the waning days of Moore's law. Moreover, the key reason for the computational inefficiency of deep learning, namely the need to shuttle around millions of synaptic weights, that remains unaddressed. So this, of course, has prompted research on genuinely non-Von-Neumann accelerators with co-located memory and processing, and in-memory computing is one of the most prominent approaches in this direction, where you just completely want to avoid moving around synaptic weights. So what is in-memory computing? Instead of shuttling around data between the processing and memory units as in a conventional computing system, we perform computation in place in the memory itself. Typically, we achieve it by exploiting in tandem the physical attributes of the memory devices, their array level organization, the peripheral circuitry, etc. In-memory computing can be viewed as a subcategory of processing in memory or compute in memory, which also includes, say, near memory computing, right? So what people typically think of as processing in memory is essentially a combination of in-memory computing and near memory computing. I think something that Nima also alluded to in his introduction. But if you want to ask me what is the difference between the two, I would say this is kind of the litmus test for me, that at no point during computation, the memory content is read back and processed at the granularity of a single memory element, right? So if you read back the memory and then you process on it, then it is near memory computing. But if you collectively compute on the memory, then it is in-memory computing. I think this kind of covers most of the cases as far as I'm concerned. Naturally, memory is at the heart of in-memory computing because we are computing using the physics of memory devices. So memory is not just a place where you park your data, but is an active participant in the computational process. In recent years, in-memory computing has been facilitated with both charge-based as well as resistance-based memory devices. I also want to point out that resistance-based memory for me is also synonymous to memristive devices. So there's also some confusion in the literature as to what is memristive and what is resistance-based. But yeah, so they are synonymous, at least for me. And in recent years, of course, as I said, in-memory computing has been facilitated with both types of memory devices, but of course, by exploiting a slightly different physical laws. You could argue that using the charge-based memory devices, it's mostly charge sharing or Coulomb's law, whereas with memristive devices, it's mostly Ohm's law, Kirchhoff's law, these kind of things. So, but we can do in-memory computing with a wide range of memory devices. Right, let's now move on to the second part where we talk about deep learning based on computational phase change memory. So there are several memristive or resistance-based memory devices that could facilitate in-memory computing and could be employed for deep learning acceleration, and phase change memory is just one of them. Phase change memory is based on this property of certain compounds of germanium, tellurium, and antimony, whereby they have drastically different electrical and optical characteristics depending on their atomic arrangement. So for example, in the disordered amorphous phase, they have a very high resistivity, and in the ordered crystalline state, they have very low resistivity. Now, if we sandwich a tiny volume of this material, so we are talking of tens of nanometer by tens of nanometer kind of volumes of material between two electrodes, then we can make a memory device out of it. By applying a voltage pulse and subsequent Joule heating, this material can be reversibly switched from the crystalline phase to the amorphous phase. And depending on the phase configuration now, the device will have different resistance values. And this in turn can be deciphered by biasing with a small amplitude read voltage. So we are essentially storing information in terms of the resistance of these devices. So there are two key physical attributes that facilitate deep learning acceleration. One of them is analog storage capability. By applying suitable electrical pulses, we can achieve a continuum, or we can achieve a these kind of intermediate phase configurations, where we modulate the size of the amorphous region. And this way we can achieve a continuum of resistance or conductance values. So you can see it here, right? It's essentially an analog storage device. So this is one property that you would use for deep learning acceleration. I'll come to it later on. The other attribute is the accumulative behavior. This is slightly more subtle. So what you do is you start from a fully amorphous reset state, and by applying a sequence of crystallizing pulses of the same amplitude now, we can progressively crystallize and achieve lower resistance values or higher conductance values. So essentially, we have a non-volatile integrator or a counter of programming pulses, right? So that's why it's called an accumulative behavior. So I just want to be clear that people understand the distinction between the two. So in this case, you really don't care how you achieve these intermediate states through different pulse amplitude or pulse duration or whatever. You are able to achieve an analog conductance state. That's all you need. But here, you really have to, this is a more stringent condition whereby you should be able to apply a sequence of pulses to progressively get lower resistance values or higher conductance values, right? So these are the two key properties. You will see later that if you want to do deep learning inference, you only need the former. You just need the analog storage capability. But if you want to do training, you also need the accumulative behavior. Note that any other, any other memory technology that exhibits these two attributes is also a viable candidate for deep learning acceleration. So, if you can find a resistive RAM device which also does it, then it's again can be used for deep learning acceleration. Right. So now let's see how these two key attributes can be used to emulate synaptic behavior. So as you know, deep learning or deep neural networks are all about networks of millions of synaptic weights. So essentially, the idea would be to emulate the synaptic weights or synaptic functionality using the physics of phase change memory devices. So both the analog storage capability and accumulative behavior will be used to emulate this, and in slightly different ways, right? It can immediately be seen that an array of memory devices, PCM devices, organized in a crossbar configuration can implement one layer of a neural network. So if you take like one layer of a neural network, it has presynaptic neurons and postsynaptic neurons, and then you have the matrix, which is holding the synaptic weights, and that is all encoded into the PCM devices here. For inference, the signals need to be scaled as per the synaptic weights and passed on to the next layer, essentially performing a matrix vector multiply operation. Now, this is what you would call a synaptic efficacy, right? This synaptic efficacy can be realized by exploiting Ohm's law and Kirchhoff's current summation law without having to read back the individual conductance values or having to shuttle them around to processing unit. So I hope it's very clear what is happening here. So if you want to implement a layer of neural network in a conventional computing system, you have your synaptic weights stored in memory somewhere. You have a processor element, a PE or elements, or a group of processing elements. You need to shuttle the synaptic weights into the PE, perform the computation, right? Get the activations and take it back into the memory. But here, the synaptic weights are fixed. They are physically instantiated. They don't move around. Instead, the data moves through the synapses. Right. And for that, the only thing that you need is the analog storage capability, because you should be able to achieve a certain synaptic weight stored as the conductance of these PCM devices. Thereafter, you are exploiting the Ohm's law and the Kirchhoff's current summation law to get that matrix vector multiply operation. So this is what I would call synaptic efficacy, and that is all what you need for deep learning inference, where you don't change the synaptic weights after you load them. But for training, the synaptic weights need to be also nudged back and forth as the network sees training examples, right? You need to change the synaptic weights. And this, I would like to call it the synaptic plasticity. And this can be achieved now by exploiting the accumulation behavior again in place in the memory array itself. Because if you want to change, if you want to nudge a synaptic weight up or down, you know that you can apply an electrical pulse and then you can change the conductance. And mind you, for this, you never have to read back the synaptic weight, right? You can just nudge it back and forth. And that is why you need accumulative behavior, because you shouldn't be able to, if you read back and then change, then you are beating the whole premise of in-memory computing, right? Because then you are getting back your memory and you're doing something on that. So that is why you should be able to blindly apply a pulse and expect it to go in the right direction. And that's why you need this, you need the accumulative behavior that I talked about earlier. So essentially, these are the only two things you need to do deep learning acceleration. It's pretty simple, right? You need to be able to emulate synaptic efficacy to do inference, and you need to be able to emulate synaptic plasticity to do training. So let's just look at deep learning inference in a bit more detail. So let's assume, so what we do here. So we have a fully trained network. We trained the network. The synaptic weights were obtained by some training methodology, most likely in software. Now these weights, I mean, the weights correspond to each layer is mapped to arrays of computational memory cores where PCM devices are organized in a crossbar configuration. Now, using the analog storage capability, we are able to do that, right? Because whatever synapse, suppose you have a W weight here, then you can find a WIJ. You can get a GIJ, which can be tuned to be proportional to WIJ, right? As simple as that. It's a nice linear mapping between the conductance of the devices and the synaptic weight. Now, each core can perform the matrix vector multiply operations, typically like in less than 100 nanosecond, corresponding to each layer. And then it can pass on that information to the subsequent layer and so on and so forth. So you can actually do the matrix vector multiply operations corresponding to each layer in order 1 time complexity. So essentially, as I said, if you say that, okay, my accelerator is only going to do deep learning inference, then you only need to focus on analog storage capability, right? You really don't care whether it has a cumulative behavior or any other property in this case. It's the simplest case. But of course, there are some key challenges. One of the key challenges is the imprecision arising from the programming inaccuracy. For example, if you take 10,000 PCM devices, experimental data, and if you try to program them into a precise conductance value, and if you look at the cumulative distribution, you always find that you have some kind of a distribution around the programmed state that you're looking for. Suppose you want to achieve 0.12 as the synaptic weight, you'll always have a Gaussian distribution around 0.12, right? So this is the programming inaccuracy that you need to deal with. But of course, even after programming, there'll be some kind of conductance fluctuations, resistance drift, conductance drift, and so on, which we may have to deal with. So there is really no guarantee that we can achieve software equivalent classification accuracy using in-memory computing. And for quite some time in my group, this was kind of the main challenge, right? To really understand, with all the effort, can we still get sufficient accuracy to solve relevant problems? But indeed, it turns out that if you use a custom training procedure, then we can indeed get ISO accuracy. So the idea is, during the training process, which is done all in software, not on hardware, right? In software, you just need to add noise during the training process. And in this way, your hardware becomes resilient to the fact that it will be operating in a noisy environment. That is really remarkable how well it works. We also experimentally verified it using PCM devices fabricated, in this case, 90nm CMOS technology. And here is an illustration of the classification accuracy. So this is now classification accuracy on ResNet 32 and Cipher 10. This is the baseline accuracy here, dot line in floating point, and these blue points here are the ones we got experimentally on PCM devices. So what we see is that if we are able to do this additive noise training, the custom training, then you can actually achieve ISO accuracy inference. In fact, we have tried this since then on several networks, even much larger than this, including even transformers, where you can get ISO accuracy deep learning inference. So this gave us a lot of confidence that even though this computation is analog and noisy and whatnot, we are still able to achieve ISO accuracy deep learning inference. So now, how do we do training with in-memory computing? So here again, the untrained synaptic weights now, because they are essentially random, they are mapped into an array of computational memory cores. As you know, when you're doing training, it involves first a forward propagation step. So that is just like inference, right? You basically do the matrix vector multiply operations in order 1 time complexity and pass on the data, just like how we would do it for deep learning inference. Now, in a similar vein, during back propagation, we have to propagate the error backwards, and that also involves a bunch of matrix vector multiply operations, but this time using the transpose of the matrix. This again, you can readily do it by inverting the point at which you apply the bias voltage. So you basically swap the pre and post synaptic neuron positions, if you will, right? And then you can do the that operation as well. So these two can work beautifully. But there's a catch. These two forward and backwards propagation stages can be rather imprecise. This is actually a result from deep learning research. However, the non-ideality associated with the accumulative behavior means that we cannot rely on the direct weight update that I talked about earlier. That means you cannot just use the simple synaptic weight update scheme that I mentioned earlier. So this doesn't really work very well. So what we have to do is we have to accumulate the updates in high precision. And whenever the accumulated weight is large enough, we apply accumulative pulses to the corresponding devices blindly without reading back the conductance, right? And this is a very sparse process. So you can almost think of it as like you have your neural network randomly initialized to the hardware, and then you accumulate the weight updates, and whenever it reaches a certain threshold, you would like nudge the synaptic weights back and forth thereafter. So this is called mixed precision training, and this works beautifully, right? So you can use it in a wide range of networks and get ISO accuracy, but it may not give the maximum advantage of in-memory computing, because you still need to do this high precision accumulation of the delta W's. So this is, but other than that, I think it's a very nice approach still to achieve. If your target is to get high accuracy, then this is the only way effectively. And I want to point out that in this whole process, the only attribute that we used is now the accumulative behavior, right? Because you start with random weights and you're nudging the weights back and forth using the accumulative behavior, because that's all you do. So that's why I said for training, you use the accumulative behavior. As I said, the mixed precision training approach works, remarkably well. Here again, there is a very simple, in this case, experimental result of a 2-layer perceptron doing handwritten digit classification, and you can see that this is right now this is now the classification accuracy as a function of the training epochs, and you can see that you're able to achieve very close to the training and the test accuracy that you would have got in floating point. And what is really nice is that once it is trained, and if you just freeze the training process, thereafter, it is a very good inference engine, right? So it is really learning on the edge what you're doing, right? You're having this in-memory hardware sitting there learning, and the moment you reach your correct synaptic weights, you freeze the learning process, and thereafter you can continue to use that as an inference engine. So this particular one, I mean, these are the measurements over, I don't know how much time it was, but this particular chip is still on the cloud and you can access it. It's almost like 2 years or something since we programmed it, and it still infers beautifully. So it was again a test of how robust these schemes are, right? So if you go to this website, you can play around with it. There's also a lot more information on how exactly it was implemented. Right. So, but now how does an accelerator based on in-memory computing would really look like? So what I talked about was about these single cores and about accuracies we can achieve. So, but if you look at a full-fledged accelerator, it would have a number of in-memory compute cores interconnected by a communication fabric. So this is just one example chip that we have fabricated, where you can have 64 such in-memory compute cores interconnected by what we call a 5x P, 5 parallel prism network topology. That's the specific reason why we did that. I mean, you can look up at this newspaper to get more details on that. Now, as you can imagine, this is a genuine data flow architecture. So the synaptic weights are stationary and the activation signals are propagated through the chip. So hence, compared to the conventional digital accelerators, this is now highly amenable to spatially pipelined data flows with a potential to achieve unprecedented latency and throughput. So you can think of it as, this is spatial pipelining, right? So if you have ResNet32 network, then you can have the different layers of the network. I believe the 34 layers or something. All of them can be mapped onto these cores, and then you can operate them in a highly spatially pipelined fashion. So you will get remarkable throughput. But also for batch one inference, it's really amazing because all the weights are already preloaded, so to speak, and literally the activations are propagating through the tiles. So that's kind of the idea here. So in this year's VLSI, we actually presented, one of these 64 compute cores. This, by the way, was fabricated in 40 nanometer CMOS technology. So it is a 256 by 256 array of synaptic weights. Each synaptic weight comprises 4 phase change memory devices representing a signed weight. So 2 PCM devices for positive and 2 for negative. There is no negative conductance, of course, right? That's why you need this differential configuration. And besides that, we have ADCs. Again, these ADCs are remarkable ADCs. They are current controlled oscillator based ADCs, which are super compact. This is another huge innovation in that paper. And then it also has some local digital processing. And you can see that the MVM performance that we get is something like 10.5 tops per watt. And 16.5 tops per watts per millimeter squared. So it's quite a, I mean, it's an experimental prototype chip. Still, I mean, these numbers are quite decent. We also got the MVM performance, which is better than a 4-bit fixed point engine in terms of accuracy. And it's again something that we could definitely improve in the coming months. Yeah, so this is kind of the latest in terms of, I would say this is the most advanced in-memory compute core in terms of integrating all aspects of it. Because we had also a local digital processing unit, which does, for example, the scaling operations and so on and so forth. So this had everything in it, right? So this is a very powerful IMC core. Okay, so now you would ask me, okay, so what's the big deal here, right? If you look at a single tile performance, we have a dimension of 0.8 millimeter by 0.8 millimeter. We operate at 130 nanoseconds. This is a VLSI paper. We arrive at 10.5 tops per watt, 1.6 tops per millimeter squared. It is good, but it's not like make you sit up and notice. But now let's just see what happens next. Suppose this 0.8 by 0.8 becomes 0.2 by 0.2, which is very doable using dense memory integration, because we are integrated in the back end way up in the metal stack. But if you come closer, if you integrate it, we can actually go to 0.2 by 0.2. If you can reduce this 130 to 50, which is very doable again. And if you change the array size to 512 by 512, we are immediately going to 100 tops per watt and 261 tops per millimeter squared. So now we are talking, right? So this is getting very interesting. But that's not the end of it. We can actually potentially go to 0.1 by 0.1. We can potentially read with 10 nanosecond and go to 1024 by 1024. And then we are reaching these astronomical numbers that you see here. So this is just if you compare one-on-one with a digital compute core. But in addition, you get the non-volatile weight storage, right? Because you're not paying any price for storing the weights. You don't need to move them in. And the weight stationarity, that you don't need to move them in, right? So essentially, this is kind of the promise that we are looking at with this approach. Now, the natural question is, okay, can we increase the computational precision? Because as I said, we have something like 4 to 5-bit precision right now. Can we get it higher? Of course, there's a lot of device level work. I won't go into details of it. One very promising approach that we are looking at is so-called projected phase change memory. It is a slightly modified PCM device that exploits the IB characteristics of phase change materials. I mean, I don't want to go into details. You can look up these papers here. But what we showed in a highlight paper a couple of years back in IEDM is that if you use this kind of geometry, this kind of device concept, you could potentially get 8-bit equivalent accuracy, which should be a game changer. So you can think of it as, having an 8-bit digital multiplication, which is 33 times less power. Which consumes 33 times less power. So there are concepts out there in the device world to try to push the compute precision even further up. What about the computational speed? Using electronic in-memory computing, a computational cycle of less than 10 nanosecond is probably rather challenging, rather even tenths of nanosecond. But if you go into the photonic domain, then 10 nanosecond is super slow, right? Because we can have a modulation speed of exceeding 10 gigahertz easily in photonics. So that's something that we have been looking at with our collaborators in Oxford and Münster, where we built a photonic equivalent of phase change in memory computing. So where we put a phase change memory element on top of a photonic waveguide, create a crossbar array based on that, and then besides the 10 gigahertz modulation speed that you get, you also have the wavelength division multiplexing capability. So we implemented this photonic processor that can now implement multiple matrix vector multiply operations at the same time. And one application that is particularly amenable to this is convolution, because the fixed convolution kernels are mapped to the photonic, the crossbar array. The input vectors corresponding to the image, as you can see here, they are encoded on multiple wavelengths derived from an optical frequency comb. So you have the kernels fixed, and then all the inputs that need to come in, all the inputs that correspond to the different matrix vector multiplications that you need to do, they are fed in parallel at different wavelengths. So at the same time, you're able to perform all these matrix vector multiply operations. So this was really amazing. So this essentially allowed us to perform convolution operations extremely fast, potentially a whole convolution operation in a single time step, which is beyond the reach of any electronic system. Yeah, so this is another way in which we could potentially go and beat this tens of nanosecond time scale that I talked about in the previous slide, right? So if you go back here, I mean, 10 nanosecond is even a bit challenging. So, but with photonics, you can actually easily beat that. So as I said, it's like 10 gigahertz is a modulation frequency in photonics. Right, so just a glimpse of some of the device level work that is going on, which could even push the frontiers of this technology. So that takes me to the last part, which is again a little bit of the forward-looking thing, and maybe also trying to give a bit more guidance as to what kind of research you should probably look into going forward, applications beyond conventional deep learning. Yeah, so one of the, one interesting paper which came up like last year was from Sarah Hooker at Google. She wrote this paper called The Hardware Lottery. Essentially, the observation was that if you look at deep learning in particular, right, I mean, backpropagation was kind of known from 1963. CNNs were also kind of around, for instance, 1982 or 89. But then, even though it was a good idea, deep neural networks, it had to wait because the hardware was not ready yet. So essentially, we lost several decades due to the lack of adequate hardware. So her suggestion is that we need to ensure that good ideas are not lost or delayed this way, right? Because there might be very interesting ideas out there which may get lost because we don't have the right hardware. And essentially that an algorithm's success is determined not just by how good it is, but whether it is suitable for the hardware that is around at that point in time. So it's always a good idea to look ahead and see, okay, what is next, and potentially what role can IMC play going forward, given that there might be some good ideas out there which we need to look out for, and otherwise they could kind of get lost, and we may have to wait another few decades for it to be coming back into prominence. So with that thing in mind, if you look at the deep learning landscape right now, what we see is that for all the tasks such as computer vision or machine translation, it almost looks like deep learning is probably the best it can get, right? I mean, already we are beating human level performance in many of these tasks. And already you see that, convolutional neural networks have kind of taken over the computer vision domain. Transformers have kind of taken over the machine translation domain. And most likely this is where it will stay for a while at least. I mean, things will improve probably, but I mean, the underlying principles are slowly getting kind of finalized. Right, but what is going on if you look at it, besides this, is that people are really looking at DNNs plus something, right? So people have realized that as far as finding correlations in data is concerned, or learning representations from large amounts of data is concerned, deep learning is probably the thing to do. But if you want to extend that to more general AI, or if you want to do something more than that, you may always have to interface deep learning with something else. You have already seen examples of that. For example, you could potentially interface that with Monte Carlo tree search or reinforcement learning, like those folks who are doing, for example, playing games like Go and so on. Symbolic AI is something that IBM is pursuing a lot, whereby they're trying to combine deep learning with symbolic AI to do more general AI, so to speak, to achieve more general AI. There's a lot of interest in associating or connecting deep learning with explicit associative memory, so that you can have more reasoning capabilities and so on going forward. So in many instances, this has significantly extended the power of deep learning to realms where we thought deep learning had no hope of succeeding. So it's a very important avenue that we all need to be looking out for. Besides that, there is still a lot of interest in more biologically plausible artificial neural networks. There's always the promise of enhanced information processing capability by having additional neuronal and synaptic dynamics, temporal codes, and so on. So if you look at the deep learning landscape, this is kind of what you see, right? It's either deep learning plus something, which many people are working on, or people are looking at more biologically plausible deep neural networks. So why deep learning plus something? I find this a very compelling demonstration of why deep learning is so limited. So essentially deep learning, essentially DNNs are rather sophisticated functional approximators. We all know that. So it's basically finding correlations, but it has no understanding at all. So for example, if it looks at a state-of-the-art deep neural network will look at this image and say it's a teddy bear, and obviously it's not. and also there's another very nice illustration from Alan Yule's group in Johns Hopkins where you take the picture of a monkey and then you put it. Without this guitar, it's a monkey for the deep neural network. But the moment you place a guitar on top of the monkey, the guitar becomes a bird, presumably because it is in a jungle environment. And what is even worse is that because the guitar became now because of the guitar, the monkey became a human being. So it's like very difficult to argue with that. It's really crazy, right? So anyway, the bottom line is that it just shows that there is really no fundamental understanding of what is going on. So clearly, all you can expect from deep learning is to get excellent learned representations, but I don't think you can expect a deep neural network to be reason or to understand or to come anywhere close to artificial general intelligence. So that is the reason why DNN plus something is going to be super important going forward. So we have been doing a little bit to work in this direction. So our approach has been to combine deep neural networks with external explicit memory, but not just the explicit memory as was already shown in neural Turing machines and so on by the Google group and also by Facebook with the memory networks, but rather we want to have the explicit memory live in the hyperdimensional vector space. And you may ask why hyperdimensional vector space. The idea is that if you can store these learned representations, or if you can make the neural network learned representations who live in a hyperdimensional space, then you can use the powerful hyperdimensional paradigm to do further stuff on top of it. It's a very nice way to combine deep neural networks with symbolic AI, with vector symbolic AI. So it's again, I don't want to go so much in the details of it, but you can maybe look up the blog article that I wrote with the bus here, or even this paper in Edge Communications, which just appeared. So the whole idea is to now combine deep neural networks and to try to make it conform to or guide the neural network to represent unrelated objects with dissimilar high dimensional vectors. So you basically have an explicit memory where each of the memory element is a very high dimensional binary vector, right? So that's the idea here. And potentially this will also address some of the challenges that I showed about with this monkey guitar problem kind of thing, where we might be able to do things like variable binding in a very efficient manner if you are able to learn representations with a certain structure. So it's a very interesting topic on its own right, but let me now stick to the computational aspect of it. The one big advantage of having in a DNN plus something, where the something is an explicit memory and that explicit memory is living in hyperdimensional space, is that we can implement that associative memory using in-memory computing. Because this kind of associative memory search, or the soft attention, is computationally very expensive in a von Neumann machine. So essentially what you're doing is, whenever a neural network comes in, it spits out a query vector. You need to compare it against the explicit memory. And this is an operation which touches every memory element in the explicit memory. And that is not very nice for von Neumann machines. But this is something that, as you know, already from that matrix vector multiplier example, this is an operation that we can do in a very efficient manner using in-memory computing. So this is one example where we actually used in-memory computing also for the DNN plus something category of problems, and not just DNN. So we can of course have the DNN implemented using in-memory computing, as I showed in my second part of my talk, but you can also have the something done using in-memory computing. Now let's look at the other key thing that is going on. As I said, is spiking neural networks, right? So if you look at conventional deep neural networks, the neurons are static nonlinear functions. Synapses are scalar multiply units, and information is transmitted as floating point numbers. But if you look at biological neural networks, neurons and synapses are dynamic entities. Information is encoded in terms of time and transmitted by spikes. The processing is asynchronous, so there's no global clock. And the learning is really not backpropagation kind of learning, but it's rather local event-based learning. And as you know, this is also what is employed, or something like that is probably closer to what is happening in the brain. I mean, so in some sense, they're very similar, I would say, but in some sense, it's quite different as well, right? Because there are some, I mean, as we all know, as we showed from the very beginning, the DNN is actually an emergent behavior which came out of connecting very simple models of the neurons together, neurons and synapses together. So in that sense, it has some biological motivation, but it is also quite different in that sense from biological neurons and synapses. For many years now, people have been trying to see, because of these added features of a biological neural network, whether it has a computational merit, right? And in fact, there are many reasons why someone would be tempted to do that. First of all, as I said, there's no global clock, it's a synchronous processing. So if there is a sparse spatio-temporal signal involved, then there could be a case to be made for energy efficiency. Temporal codes can have ultra low latency. Again, this, I don't know if many people have really seen this in a correct way, because the idea is that when you are, for example, you're looking at a image processing deep neural network, then you are processing frame by frame, right? You process one frame, then all the data goes into the next one, like the picture that I showed earlier, even with IMC. But if you are just relying on spikes, then you can have one spike just propagating through the network without having the frame-wise processing happening. So this is why you may have a potential for ultra low latency. There's some nice work from Simon Thorpe and so on, where he showed, how the human visual cortex can detect objects extremely fast because of this property. And he also had the rank order coding and some of these ideas proposed in order to show that. Local event-based learning is supposed to be much more energy efficient than global learning schemes like backpropagation. So there's a lot of interest there. But one thing that in our group we have been looking at is the synaptic dynamics, because as I showed earlier, in a conventional neural network, a synapse is just a weighting of the signal. But in reality, you have some dynamics, so which means that you should be able to have some computational superiority, right? If you have this additional synaptic dynamics. So this is something that we recently looked at in some detail. Our whole idea was to try to understand how, with an additional synaptic dynamics, are there any problems that might be interesting that we could solve? And one of them we found was this problem of detecting objects in continuously varying environments. In this case, for example, you have an MNIST data set where a deep neural network will do amazingly well. But then if you start showing these kind of occlusions in front of it, then the conventional deep neural network is completely confused, and it will start becoming very erroneous. But if you can add a tiny bit of short-term synaptic plasticity into the synapses, right, then you can immediately recover your classification accuracy. So this was actually a very nice illustration of how a spike neural network with what we call short-term STDP, spike timing dependent plasticity, can deal with these kind of issues where you have occlusions or some kind of things going on, right? And then you can get this robustness back. So I would strongly encourage you to read this archive paper to get more more into it. And frankly, I haven't seen too many such demonstrations where people have shown the computational superiority of spike neural networks in a specific task. And it's also very clear that if you're just looking at standard image recognition kind of tasks, it'll be very difficult for spike neural networks to outperform conventional deep neural networks. But these kind of special problems are probably the ones where they will outshine the deep neural networks. So now where does in-memory computing come into play here? Actually, it is not too difficult to implement or to extend the concepts from conventional deep neural networks to the spiking domain when it comes to IMC. The synaptic efficacy and plasticity can be realized again using the physically instantiated synaptic arrays. Not much of a difference there. It's just that your input encoding is now spike-based, and your neurons are slightly different, but it's essentially almost this very similar concepts can work for when you employ in-memory computing for spike neural networks. So here was actually a recent demonstration where we mapped audio signals to images. It is actually IBM passed through the cochlea from IMI instead of neuroinformatics, and then you can actually convert that audio signal into images. So it's actually done by a supervised learned spike neural network in this case. But I just want to point out the last part. What I want to say is potentially, but we could implement more efficient, intricate synaptic dynamics using in-memory computing. That would be the real power of in-memory computing for spike neural networks. But for that, first we need to have algorithms which are showing sufficient promise for you to go ahead and start doing these things in in-memory computing. But again, I just want to point out that since we're looking at, potentially, maybe like a very interesting algorithms comes up from the spiking domain, it could again hit that hardware lottery problem, right? So maybe the hardware is not there for it to be enabled, and that's what maybe at least some of us have to look into, right? Try to come up with good solutions to do that. Right. So with that, I would like to summarize. So deep learning is a key driver for innovations in computing systems, as you know, and new forms of computing such as in-memory computing are being explored. So attributes such as synaptic efficacy and plasticity can be implemented in memory by exploiting the physical attributes of memory devices such as space change memory. ISO accuracy, DNN inference, and training is possible within memory computing. So recently fabricated mixed signal IMC cores demonstrate the promise of this technology. Concepts as projected memory and photonic in-memory computing could significantly improve the computational precision and performance going forward. The IMC approach could also impact applications that transcend conventional deep learning, such as memory augmented neural networks and the spiking neural networks. So much of the work that I showed was done by my team in the in-memory computing group here in IBM Zurich. I would also like to thank my colleagues from around the world, the worldwide labs of IBM, in particular the IBM AI Hardware Center, which is a collaborative research hub headquartered in New York. I'd also like to thank several of my academic collaborators and also general support from European and Swiss funding agencies. But before I conclude, I just want to also present to you like this analog AI hardware acceleration toolkit. This is an open source toolkit from us. I think it would be really great if some of the students in TU Vienna and elsewhere could also contribute to that and try to build on the work that has already gone into it. I think the whole idea is to kind of develop algorithms and software to kind of absorb these kind of in-memory computing hardware and also to make them ISO accurate in many cases, right? It's an extension of the work that I showed already in today's talk. So with that, I would like to conclude, and I would like to thank once again Nima for the opportunity to speak to you, and looking forward to the discussions that follows.